In the seventh lecture, we will discuss about the remaining part of cone penetration test, and then I will discuss about the other in situ test. So, in the last class, in the sixth lecture, I have already discussed about the some part of the cone penetration test. I have discussed the static cone penetration test. And now, today I will discuss about the static cone penetration test, the remaining part of the static cone penetration test, and as well as I will discuss about the dynamic cone penetration test. So, I have already discussed these things that in the dynamic cone penetration test, which is similar to the SPT, where we are applying hammer blows or blows to drive the cone into the soil, like SPT that we are applying the blows to drive the sampler tube into the soil. And but in static cone penetration test, we are not driving the cone, we are basically pushing the cone into the soil with a particular rate, and that rate is given generally 1 centimeter per second. But in the SCPT, static cone penetration test, we are getting continuous measurement, but in the dynamic cone or the SPT, where the hammer blows is required. So, we are getting the data with certain interval, and that is generally not more than 1.5 meter depth interval. And but in the difference between the SPT and the cone penetration test, that in the SPT we can collect the soil sample, but in cone penetration test, whether it is SCPT or DCPT or dynamic or static, we cannot collect the soil sample. And another difference in between the SPT and the DCPT or dynamic cone penetration test, that in the SPT the borehole is required, but in the dynamic cone penetration test or any cone penetration test, the borehole is not required. So, next one I have discussed already this part, that is the 4 major parts in that a cone, the sounding rod, mental tube, friction jacket assembly and cone assembly. First, the cone assembly with sounding rod is pushed with a 40 millimeter, and then we will get the cone resistance, and then this is the second position. Then the sounding rod, friction jacket assembly and cone assembly, these 3 all are pushed into the soil further 40 millimeters. So, here we will get the total resistance. So, from the total resistance, if I subtract the cone resistance, we will get the friction resistance. So, that is why we can separately calculate the cone resistance and the friction resistance. In the next part, we will push the mental tube by 40 millimeter, and in the fourth stage, we will push mental tube and the friction jacket assembly further 40 millimeter, so that we can bring it to the original condition. So, I can show you one particular YouTube video, and the link is already displayed in the screen, that here this is the first stage where it is pushed by 40, and the further the total one is pushed by further 40, and then the total system is taken into original position. Then the next one will go for the next depth where we want to take the data. So, first 40 millimeter for the cone resistance, then the next 40 millimeter for the total resistance, then we will bring the total system again in its original position. So, this way these things will continue, and the same thing we can do in the field. I have the video, the same one. First the cone resistance we measure, then the total resistance, then finally, if we subtract the friction cone resistance from the total resistance, we will get the friction resistance. So, these are the testing methodology. Here we are measuring the resistance that this is the instrument, and this is it is pushed into the soil. So, once we get the resistance, then the next step we have to determine the soil properties. Those properties will be required for our foundation design. So, for the clays, the Cu value, undrained shear strength or undrained cohesion of the soil, this is undrained shear strength of soil. So, here the Cu value is given, Qc is the cone tip resistance or cone resistance, or sometimes we call it tip resistance, and sigma v, remember that it is total vertical stress at a depth of penetration, and Nk is the cone factor. So, if I use the electrical cone, then it is 15, if I use the mechanical cone, then it is 20. So, Nk value is in between 15 and 20. So, this value you can take any value in between this range depending upon which cone we are using. So, but remember that it is the total vertical stress, it is not the effective vertical stress. So, this way this correlation is given. So, but for the sandy soil, if it is a sandy soil, then the friction value or the friction angle, the phi is the friction angle, we can get with this relation. So, here it is log Qc is the cone resistance and sigma v dash. So, here sigma v dash, or sometime as I mentioned we can we put it as a P0 dash, it is the vertical effective overburden pressure or stress. So, initial one in case of clay, it was the total stress, but now it is the effective stress. So, and I have already discussed that how we will calculate the effective stress, I will calculate the total stress. Total stress, suppose if it is saturated soils, total stress will be the unit weight, saturated unit weight into the height, but if it is the effective stress, then you have to subtract the pore water pressure. So, that means we take the submerged unit weight of the soil into the depth. So, these two correlations we can use to get the cohesion value and friction value of the soil based on the cone resistance. So, and we have charts also, by which also we can determine what would be the relative density of a soil. If I know the cone resistance, suppose if I know the cone resistance and 30, and if I know the vertical effective stress, so we can get what will be particular relative density. So, that will be the 80% relative density of a soil. Similarly, if I know the cone resistance, if I know the vertical effective stress, then we can get that, suppose it is 30 is the cone resistance and vertical effective stress is 150 kilonewton per meter square. So, that means the phi value will be 44 degree. So, this way also we can use this chart and get the phi value and the relative density of a particular soil. Next one, we can calculate the friction ratio. This friction ratio is the slip friction or the friction resistance divided by the cone resistance. So, if I know the friction ratio, then we can use this chart where the friction factor, this is friction factor and this is the cone point resistance or cone resistance, it is in meganewton per meter. So, if I know the friction factor, if I know the cone resistance, so suppose the friction factor friction ratio is 3. So, if the friction ratio is 3 and we have the cone resistance is 0.4 meganewton per meter square. So, and this is 3. So, soil will be the clay silt or the silty clay. So, the type of soil also we can determine based on by using this chart if I know the friction ratio and if I know the cone resistance. Next one is the piezo cone. So, nowadays with the static cone we measure the pore water pressure also, because here the porous stone for the pore water pressure measurement unit is attached. So, we can measure the cone resistance, we can measure friction resistance, we can measure pore water pressure, and we can measure the friction ratio. So, this is a particular typical example. So, this the reference is given. So, where we can get a particular depth, that this is the variation of cone resistance with depth, the blue one. Red one is the variation of the friction resistance with the depth. U is the pore water pressure variation with the depth, and RF is the friction ratio variation with the depth. And these are the different types of soil. So, we can get the continuous data, and then from this data we can get these plots. Finally, we will get these plots, and then from this plot particular type of soil we can get, if we know the values, we can get the our required soil properties for the design. That can be equation, that can be friction, or we can identify the soil, we can get the different properties based on the use the charts or the correlations that I have shown. So, next one is the dynamic cone penetration test. So, as I mentioned, so this is the IS 4968 part 1 1976, where we have to apply the hammer blow. So, the equipment consists of a cone, driving rod, driving head, then host equipments, and the hammer to drive the cone into the soil. So, the hammer used here, which is a weight of 65 kg, and is a free fall is 75 millimeter or 750 millimeter or 75 centimeter. So, the height of fall is 75 centimeter or 750 millimeter, and the weight of hammer is 65 kg. And the number of blows for every 100 millimeter penetration of cone is recorded, and the process shall be repeated till the cone is driven to the required depth. So, and better than the SPT, the dynamic cone penetration test, which is better than the SPT or SCPT in hard soil such as dense gravel. And so, here also we have to use available correlation to like SPT to with the number of blows to get the soil properties. So, we can see these are the two SPT and the DCPT, dynamic cone penetration. This is the cone of the dynamic cone penetration, which is solid, and this is the SPT sample, which is hollow. So, here we can collect the soil sample, and here we cannot collect the soil sample. So, next, so the next test, so that was the cone penetration test, SPT, SCPT and DCPT. The next one that I will discuss about the pressure meter test, which is also very useful to determine the soil properties. It is also an in situ test, where the pressure meter consists of a cylindrical probe. So, this is a cylindrical probe, or this is actually the pressure meter. You can see, or I will show you a video where also you can see the pressure meter. So, where there is a cylindrical probe, and which is connected with a water reservoir, and the expand cylindrical probe inside a borehole, and then probe presses the wall of the borehole, so that soil began to deform. So, basically here we are inserting a cylindrical probe into the borehole, and the cylindrical probe is attached with a water reservoir, and we apply the pressure, so that the cylindrical probe inside the borehole can expand, and it will press the soil wall in the borehole, and the soil will start deform. The volume of deformation of the borehole is measured by the fall of the water, because we have attached it with the reservoir. So, the borehole deformation is measured by the water level difference of the water reservoir. So, that is the typical description of this pressure meter. So, so this is the IS code which describes the use of pressure meter. So, here we apply the pressure through the probe onto the soil wall. So, well start deform, and the deformation is measured, the deformation or the volume change, this volumetric deformation or the volume change is measured with the help of this water pressure, water level difference. And I can show you one particular video for the, this is the pressure meter, which is these things will expand, and these are the two gut cells. So, this is the membrane that where we will apply the pressure, and it will expand, and is the soil will start deform, and we can measure the volumetric deformation with the help of the water level difference. So, this is pressure meter, and this is the typical figure where this is the measuring cell or the cylindrical probe, and you will apply the guard cell to protect this cell in two sides. So, in the video also I have shown you, there is a in the front side and the back side, you can see in the video. So, this is the protection that we are giving. So, in the, and this is the your measuring cell unit, and we can see that after that we will get this type of curve finally. So, this is the total cavity volume. Cavity volume is that the borehole or the cavity that is created. So, total cavity volume, because as we apply the deformation on the soil wall, the volume of the cavity will or the borehole will increase. So, this is the total cavity volume, and it is the pressure that we are applying. So, we are applying the pressure and we are measuring the volumetric deformation or the volume change. So, this is the total volume of the cavity, and this is the applied. So, we can see this is the typical curve. So, in here we will have three zones basically, zone 1, zone 2 and zone 3. So, here V0 is the initial volume of this pressure cell. So, V0 is measured, and probe, this is the volume of the measuring cell or the probe, cylindrical probe V0, capital V0, and we insert this thing in the borehole. The pressure is applied in increment and volumetric expansion of the cell is measured. So, we apply the pressure and the volume increases, and we measure the volumetric expansion. So, that is, and that is why you will get the pressure versus volume curve. And this is the zone 1, which is known as the reloading zone, because what is the reloading zone? So, when the borehole is constructed, so what will happen, that the soil will, so that means the soil will, so initially there is a volume of the soil wall. So, when we remove the soil from the borehole, so there will be a expansion of this wall. So, that means the borehole, when we apply the pressure, so that means this soil again go to its original position. So, initially when there is a soil wall, so initially suppose this is the original actual pressure volume of the or the side wall of the borehole. So, when we remove the soil, so there is a, these things will come in this portion. So, that means there is a expansion of the or the deformation of the wall, and this soil volume or the cavity volume decreases. Now, when we apply the pressure into the cavity, so this soil will again go to its original position. So, that is the, this zone is called the reloading zone, and P0, this point P0 represents the in situ total horizontal stress, because that is the original condition of the borehole because of the removal of the soil. So, suppose this is the original condition of the borehole, we have removed the soil. So, borehole will shift in this direction, borehole. So, this is the, say, borehole soil will deform in this direction. So, this is the original surface. Now, this is the deformed surface. When we apply the pressure, it will go to its original condition again. So, this is the reloading zone, and from here this is the zone 2. If you look at this pressure versus volume curve, it is almost linear. So, that is why this zone is called pseudo elastic zone. So, that is the linear relationship between the pressure and the volume. And then the zone 3, which is called the plastic zone, here PL represent the limit pressure. So, now this expansion of the probe, it continues unless there is a failure in the soil or the pressure or the expansion or the pressure it reaches its limit. So, that of the instrument. So, generally the failure is considered when the expansion is 2 times the total volume of the cavity in its original condition. So, now if you look at this figure, so the actually the original condition, the volume is capital V 0 plus V 0, because V 0 is the volume of the probe, and now we apply deformation. So, volumetric expansion is small V 0. So, the total volume of the cavity in its original condition was capital V 0 plus small v 0. Now, we can go up to the failure is 2 times of original volume of the cavity, or that is V 0 plus capital V 0 plus small v 0. So, and then we can get the PL from corresponding to this curve. So, generally this PL is calculated or determined by interpolation, because we know we stop it the volume and then we get the PL, or if it reaches the maximum limit of the instrument, if the pressure reaches the maximum limit of the instrument, then we stop the experiment. So, now how we will identify these 2 points? So, these 2 points, we identify these 2 points where the pressure versus volume relationship is linear, and this portion is the left side of this linear zone, or the pseudo elastic zone is the reloading zone, and the right side is the plastic zone. And we corresponding to this 2 point, V is the small v 0 and P is the small pressure is the small p 0, and corresponding to this points volume is the V 0 plus small Vf, Vf is the final, and corresponding P is the Pf, or that is the this is noted as the Pf. So, here we have P 0, Pf and PL, and here the capital V 0 is the total original volume of the cavity probe, and then there is expansion of amount of small v 0. So, this is the total volume of the cavity, capital V 0 plus small v 0 at the original condition, and the final condition we have 2 times of capital V 0 plus the small v 0. So, that is treated as a PL, or the limit pressure. So, once I similarly again from here we can calculate the pressure meter modulus. So, this expression is given. So, where as I mentioned that capital V 0 is the volume of the measuring cell or the probe, it is taken as 535 centimeter cube, and the Poisson mu is the Poisson ratio, Vm is the average volume of the initial and final. So, this is the V 0 plus Vf divided by 2, and del P is the difference of pressure, that is Pf minus P 0, and del V is the difference of the volume, that is Vf minus V 0. So, and as mu is the Poisson ratio, and V capital V 0 is the measuring cell volume, as I mentioned. So, from here we can calculate the pressure meter modulus, and then we have to apply the correlation. By these correlations we can get the soil properties like the other in situ test we are doing. So, that is why this undrained cohesion of the clay can be determined that PL minus P0 divided by NP. As I mentioned, PL is the, this is the PL, which is the limit pressure, and P0 is the pressure, that is we can get in situ horizontal stress, or that we are getting corresponding to this point. So, that is the PL minus P0, and NP is the typical values which varies between 5 to 12, and average value 8.5 can be taken. Now, this pressure meter modulus can also be correlated with the field measured SPT values, and this correlation is given. This is for the clay and this correlation is for the sand, by which also you can determine, if I know the n value, you can determine also pressure meter modulus, and or otherwise we can determine the pressure meter modulus with the help of this expression. Now, the next test that I will discuss is the dilatometer test. Here also this is also another in situ test, where it is advanced. Again, it is pushed into the soil with a rate of 20 millimeter per second. So, here also we have to inflation of the membranes will take place, and we use the nitrogen tank to inflate this membrane. So, this is a small membrane and this is the membrane. So, this is a 60 mm diameter flexible steel membrane. So, this with the help of this inflating we have to inflate this membrane, and then based on that we get, again here also we will get the P0, we will get the PL, this is the limit pressure, and then we can by using the correlation we can get Cu, K0, OCR, all these soil properties. Okay. And then we can there are also a similar to the cone resistance, we have the chart. By this chart we can get the soil properties. So, I will give you only the correlations by which we can get the values. So, I can give you the, I can show you one video. So, this is the typical values. So, typical dilatometer setup. Yeah. So, this is the sound, this is the rod. So, if depending upon the where you are trying to measure the properties, we have to add one by one rod, so that we can increase the, this is the dilatometer, and so this one is this, if you have if you want to do the test for a higher depth, then you have to attach the more number of rods, so that this instrument can reach up to that depth. So, and this is another rod is attached. So, this is the instrument which is basically pushed into the soil. So, this is the thin membrane that was, so it is pushed into the soil. So, it is pushed, and then the corresponding readings are, and then we increase the depth of the or we increase the depth of the instrument by attaching the this rod, and then we can measure the data. So, once we get these values, so we can use some correlations to get the K0, OCR, Cu. As I mentioned that Cu is the undrained cohesion of the soil, and so your K0 is the earth pressure, coefficient of the earth pressure at rest. So, here this is the correlation. K0 is Kd by 1.5 to the power 0.47 minus 0.6. So, Kd you will get from here. So, here this is P0 minus U0. So, P0 is the contact stress, and PL here is the expansion stress. So, here when there will be a contact, that is the that portion stress. Now, when we apply the extension or the expansion, we apply the expansion of this membrane. So, that stress is PL, and then U is the pore water pressure, and from these two expressions we can get the Kd and Ed. So, if I know the Kd and Ed, these two parameters, then we can calculate K0, the coefficient of earth pressure at rest. This coefficient of earth pressure I have not I will discuss in detail when I will teach about the lateral earth pressure theories, where you will find there are three types of earth pressure, that is active, at rest and passive. So, this is the at rest. So, this coefficient of earth pressure at rest we can determine, you know, that is the Cu is the undrained cohesion. So, that also we can determine, and E is the elastic modulus of the soil, and here Cv bar is the effective overburden pressure or the stress. V means the vertical. So, we are talking about our vertical. So, this expression we can use for the normally consolidated clay, and for the over consolidated clay we can use this correlation. This is normally consolidated clay, and then this is into the 0.5 Kd to the power 1.25. And as we know what is the normally consolidated clay, what is the over consolidated clay. So, we have already discussed, and the over consolidated ratio is the ratio basically which is the Pc divided by P present, or so that means this is the OCR ratio. Pc is the past maximum stress the soil is experienced, and P present is the present test. Now, for the over consolidated clay, this value is greater than 1, and for the normally consolidated clay, OCR value is taken as 1, or over consolidated ratio is taken as 1 for normally consolidated clay. So, now these are the all expressions that we can use. Now, we have a typical problem that we will solve here, that we have done a dynamimeter test was conducted in a clay deposit. The groundwater table was located at a depth of 2 meter below the ground level. At a depth of 7 meter below the ground level, the contact pressure P0 was 280 kilonewton per meter square, and the expansion stress PL was 350 kilonewton per meter square. Determine the K0, OCR, E, assume mu Poisson's ratio is 0.35, and saturated and bulk unit weight is 20 kilonewton meter cube and 18 kilonewton meter cube respectively. So, that means we have a soil. So, this is the ground level or GL, and the water table position is here, which is 2 meter below the ground level, and unit bulk unit wise it is given 18 kilonewton per meter cube, and in saturated unit weight is given 20 kilonewton per meter cube. So, at a depth of total 7 meter, the dilatometer test was conducted, and here we have to determine the K0, OCR and E of the soil at a depth of 7 meter at a point of say A from the ground level. So, these are the so we know the Kd expression is given. So, these are the expressions of Kd, Ed. So, we will use these expressions. I am just putting directly those values there. So, we have, so that is why the Kd expression, if I put the value that this is 280 minus the pore water pressure. Pore water pressure is 7 minus 2, because and then unit weight of the water is 10, because here this is the ground level and this is the 2 meter below the ground level water table, and we are measuring at a point of A, which is 5 meter below the ground level. So, our pore water pressure U0 or U will be 5 into 10 into 50 kilonewton per meter. So, this is the 10 is the unit weight of the water. and then divided by, this is the effective vertical stress. So, effective vertical stress is 2 into 18 for the 2 meter plus again 7 minus 2, and you have to use the submerge because it is below water table. So, this will be 20 minus 10. So, the Kd value is coming out to be 2.67. Similarly, the Ed value in kilonewton per meter square, if I put this expression, this will be 34.7 into 350 minus 280, and this will give you 2429 kilonewton per meter square. Now, if I use the K0 expression, so K0 is equal to 2.67 divided by 1.5 to the power 0.47 minus 0.6. So, K0 value is coming out to be 0.71. Similarly, the OCR value is equal to 0.5 into 2.67 into to the power 1.6. So, OCR value is coming out to be 1.6 because it is over consolidated clay, that is why OCR value is greater than 1. So, similarly, elastic modulus of the soil E we can get 1.35, that is mu square into 2429, and that is equal to 213145 kilonewton per meter square. So, by using this the dilatometer test data, we have to calculate the Kd and the Ed, and then based on that we calculate all other required parameter for the soil of a particular depth 7 meter below the ground level, and here water table is 2 meter below the ground level. So, now here I am finishing this lecture. In the next lecture I will give you a summary of the all these tests that I have discussed, and then I will go for the next part, that is the sampler, different kinds of sampler, and to collect the soil sample for disturbed or undisturbed. Thank you.